Okay, good morning, lads and ladies. Welcome back. Today we're going to pick up where we left off before exam one. So I'm very excited because the section we're moving into is one that is near and dear to my heart. Today we begin talking, about polynomials. So we're moving into the middle part of this class now, the second big chunk of this class. And the sort of feel, the thing that we're going to be doing here is we're going to be doing a detailed study of certain function types. So thus far, we've studied functions in great generality, right? Like when we prove a theorem or discuss a theorem or something like that, we're saying, let f be any function, and then we proceed. Now we're going to take all that stuff that we've learned about functions and we're going to apply them to specific families of functions. So some of the things we're going to be talking about, like quadratic functions, are stuff that you've seen before, but we're going to try to take a slightly higher brow approach, the slightly new and more elevated perspective we have on functions, and look back at some of those old things while introducing a bunch of new things. I think most of what I'm going to cover today is stuff that you'll have at least seen and heard in one sense or another, but hopefully I'm able to give you some new ways to think about it, some slightly, like I said, elevated perspectives on it. Let's do the thing. I know you guys are anxious to get your tests back. I have not graded all of those yet, but my goal is to get them in by tomorrow. So your test grades as they appear in Canvas, of course, are incomplete. None of the free response questions have had the grades added yet. So I'm working through the written work. It's shown up in a few different places, of course, the physical stuff from the testing center for those who took it there, and then the scanned versions for everybody who took it online. So far, I haven't run into any big issues, but we just got to get that done. So let me make an announcement about that. So this is MAC1140, section OR1, which means we're talking pre-calculus. And today is the 29th, is that right? I think it's the 29th. Yeah, 29th. All right. So what were we going to do? Oh yeah, talk a little bit about the tests, right? So I got a few emails from people who are kind of panicked, saying, "Oh my God, my test score is this, and should I drop the class?" Please do not panic. The test scores have not been added yet. So the scores that you see in there, that's just for the true, false, and multiple choice, right? You haven't had any credit for the free response problems in there. I am going to try to get those in by tomorrow. That's my goal. But the general rule is 1 week. So worst case scenario, you'll have to wait until next Monday. All
right. If we still have to take that online, so you said we have to check in with you.
Yeah, let's talk about that too. That can go in here also. Grade it. No later than next Monday. But hopefully tomorrow, because I've got a bunch of these things that I'm pounding out tomorrow. So if I can get yours done, then I will. Yeah, if you missed the test for whatever reason, so take a look at this announcement in our Canvas course. If you happen to miss the test, if you happen to have missed the test for whatever reason, I still want you to take it. So I'm going to be doing 2 makeup sessions. One's going to be in office hours today. One's going to be in office hours Friday. So I had some people who couldn't take it today. I had some people who couldn't take it Friday. You got to be flexible. These will be the last chances to take the test, though, unless you have some sort of documented excuse, right? Something doctor's note or whatever. Just show up. Just show up to the office hour, right? So if you miss the test, just show up to this afternoon's office hour or this Friday's office hour, and I will get you squared away. You'll need to take the test right there, right then. It'll be done online using the same sort of procedures that I did for people who elected to not take it in the testing center. That means, you got to have honor lock on your computer, you got to have Zoom on your phone. The rules are exactly the same as the original test, nothing fancy. But yeah, you don't need to make any sort of special arrangements. Just show up to the office hour and say, hey, I still need to take the test.
Can we still take it in the testing center or just online now?
And I think the makeup, I want you to just do it with me online. The testing center is really overwhelmed these days, and I would have to give them a call and run through things. We'd have to know exactly who's going to be there. It'd be more complicated. So yeah, I would prefer you just take it with me online. If
Sounds
that's
good.
a problem, if somebody's like, oh shit, well then I can't do it. Please email me. We'll figure something out. But yeah, if it's just a matter of convenience or preference, I would much prefer you take it with me online. The makeup is just for folks who missed the test. If you missed exam 1. Okay. Any other questions about the test or kind of procedural stuff where we are right now? Okay, then. Let's go ahead and get started. So today, we're going to talk about quadratic functions. Which is section 3.1. And we're going to begin the section on polynomials, which is section 3.2. And you'll have a new homework coming out later today with these two sections, at least the quadratics and maybe some of the polynomial stuff on it, depending on how far we get. Let's get to it. So I know you've all seen quadratic functions before. We've been playing with one of them as a parent function so far this semester. So I'll try to keep this interesting. I'll try to avoid saying a bunch of things that you know from middle school.
I have a question about next week.
Sure.
Is exam 2 next week or the week after?
Probably we will not finish the material that's relevant for exam 2 until at least the end of next week. So we're a little bit behind what the syllabus says. But I will let you know. So once we're about a week out from exam 2, once we finish that material, I will let you know then. We can take a look at the syllabus together now, I guess. So since there are questions about the timeline, we should do that. All right. So quadratics, polynomials, dividing polynomials, real zeros of polynomials, complex zeros of polynomials, rational functions, polynomial and rational inequalities. So 3.7 is the last bit of material on exam 2. And given that we are right now like here-ish, and this is the week after that, I'm thinking we're going to need like 1-2 more weeks before we're done with the material for exam 2. So probably not the end of next week, but the end of the week after that, we will be done with that material. So we'll be ready for that test somewhere around the week of the 18th, either early the week of the 18th or late the week of the 11th, like around the 5th. You guys don't meet on Fridays. Yeah, probably around the 18th of October. All right.
Okay, thank you.
Yeah, of course. So a quadratic function, everybody knows this, but the terminology that your book uses is maybe a little bit different. So pay careful attention to the word usage. A quadratic function is one which can be written of x equals a times x squared plus b times x plus c. All right. In kind of regular math speak, it's a degree 2 polynomial. It's a combination of powers of x, where the largest power of x is x squared, and lower powers of constants are allowed. A, b, and c are numbers. Everybody has seen this before, right? The graphs of these things are parabolas. Most textbooks call this the standard form, but your textbook does not. Your textbook says that the standard form of a quadratic is f of x equals a times x minus h all squared plus k. This is the thing most people call the vertex form, but your textbook calls this the standard form. Your textbook doesn't give a name to this, this form here, so I'm not sure what they would want us to call it, but I just want to let you know that in some of the homework questions, they'll say, you know, put this quadratic into standard form. When they say that, they mean the vertex form, this thing. The reason most people call this thing the vertex form is because you can get a lot of information about the graph from this form. Specifically, you can tell where the vertex is. So I put standard form here in quote bunnies because it's not the standard thing for standard form. But then the normal pictures, you know. The graph of such a function looks something like this. If a is positive, the graph will look like I've drawn it here. The shape is called a parabola. And this point where the graph turns around is called the vertex. And it's usually labeled with coordinates h, comma, k. That h is this h, that k is this k. If a is positive, a is called the lead coefficient, and it's the same number whether you're in standard form here or this other form here. If a is positive, then the parabola is said to open up. So that's what this picture is. The shape here is called a parabola. It's an interesting shape. You can define it purely in terms of geometry, but everybody's seen it before, so I'm not going to harp on that. This is called opening up because the kind of open side of the parabola is facing the top. And on the other hand, if a is negative, then the parabola will open down. So if you're opening down, then the thing looks like this. We still call this point the vertex. And its coordinates are still h, comma, k. Like we said, if a is negative, the parabola opens down. And that's what this looks like. So if you have the thing in this quote unquote standard form, this thing we usually call vertex form, you can right away sketch a pretty decent graph, right? You just read off your vertex as h, comma, k. You look to see whether your lead coefficient a is positive or negative, and then you draw a parabola, either opening down if a is negative or opening up if a is positive with the vertex at h, comma, k. There's other information that we often would like to have, like it's nice to know these x-intercepts, it's nice to know a little bit more, like just some other points that are on the graph. But if you have this, you can immediately sketch a reasonable graph. And I want to point out that the reason that this thing tells you where the vertex is is that this is a transformation. This is of the parent function y equals x squared. So if you look at the ax squared plus bx plus c, it's very hard to see this as a transformed version of x squared, right? This does not look like x squared with some transformations applied. But the standard form, the thing that I've, with the h's and k's down here, that thing does look like a transformed version of x squared, right? So if I gave you, let me cover up the a here really quick. Suppose I just gave you this and told you to tell me what transformations do I need to apply to x squared to get this guy? What would you say? Are there any shifts, any stretches?
You're shifting right h.
Very good. So I take x squared, and then because of this minus h inside, I would shift to the right by h units. Okay, and then
Shift up by k.
yeah, exactly. So this tells me shift to the right by h units, and this tells me shift up by k units. Well, look at this thing. If x squared, here's x squared over here, right? If I shift that to the right by h units, it would look like this. And then if I shift that x squared up k units after shifting right by h units, it would look like this. This thing really is just a transformation of x squared. And that's why it's so convenient to read the vertex off from this. All right. So given this form, easy to draw the graph. Once you have the graph, easy to answer lots of questions. How do you get into this form? How do we get from ax squared plus bx plus c to a times x minus h squared plus k? This is a question that you answer in college algebra, but the answer kind of sucks. One way to do it is to memorize some formulas for h and then kind of run through a fairly irritating and disconnected process to find the constants a, h, and k that appear here. Rather than telling you to memorize some formulas, I'm going to show you a very general procedure for taking a quadratic in this form and rewriting it in this form. That procedure is going to be not just important to us here, but it's going to be important to us later when we talk about conic sections, and you'll use it in calculus. Does anybody know the name of that procedure? It's called completing the square. So the answer here is so I'm going to teach you how to complete the square, and that's really the only new skill that shows up in this section. Completing the square can feel a little bit weird the first few times you see it, so you'll need to practice this. It is something I'm going to ask you to do on the test, so please don't try to lean too hard on a formula-based approach if you happen to remember one of those. Please do actually practice this new skill. All right. I think the best way to do this is just to show you examples. So what we're going to do is let f of x be 2x squared minus 12x plus 13. And we're going to do a few things. First, we're going to put this in standard form. standard aka vertex form. We're going to find the vertex, sketch the graph. And we're going to find domain range. All right. So for part A, this is the main thing. F of x is, start just writing it down, 2x squared minus 12x plus 13. So the numbers A, B, and C, A is 2, B is negative 12, C is 13, right? Okay. I'm about to show you how to complete the square. What it means, so completing the square, what that means is that you want to take your quadratic and rewrite it as a perfect square of some binomial. And then, you can have some constants outside. But the goal is to go from something like this that has x squareds and x's in separate terms and rewrite it as something that just has one x here inside this binomial, all of which is being squared. Things like this, like x minus 2 squared or x plus 1 squared, are called perfect squares, right? It's a perfect square binomial. It's not x minus 3 times x minus 2, it's x minus 2 times x minus 2. It is a square in the same way that 9 is a square, 3 times 3. But here it's a square of a binomial. That means the terms which are going to be involved are these two, right? The x squared here and the 12x here. The 13 really isn't super important to the completing the square process. What I want to do is see what's necessary to rewrite this thing as possibly a constant times a perfect square. So if it's not already the case that a is equal to 1, you should factor out a. And you can factor it out from the whole thing or just from the first two terms. Your book just factors it from the first two terms. So if I factor out a 2 from 2x squared minus 12x, then I get x squared minus 6x. And then I'll follow the book's lead and leave the 13 out of this whole procedure. And now the idea is we focus on this. X squared minus 6x doesn't factor as a perfect square. It's x times x minus 6. But if I had the right number at the end, like x squared minus 6x plus 2, or x squared minus 6x plus 9, or x squared minus 6x plus 7, for some number that I could kind of insert here, that trinomial, x squared minus 6x plus that thing, would factor like this. So what we have to do is find that number that I need to add in here that would allow this to factor in the form I want. I call this thing the magic number. So the magic number is something that we're going to add in here that will allow us to factor x squared minus 6x plus that thing as a perfect square. The way you find it, you take b over 2a, where a, b, and c are these original three numbers. You take b over 2a and you square it. It's the only memorization step in the whole process. B over 2a and you square it. So b is negative 12, a is 2. So that's negative 12 over 2 times 2 all squared. That's negative 12 over 4 all squared. Negative 12 over 4 is negative 3. So this number is 9. So you factor out the lead coefficient from the first two terms, and then you compute your magic number. Once you have the magic number, you put it in where we want it. So I claim that if we have x squared minus 6x plus 9, this thing factors as a perfect square. But if I'm going to add a 9 in here, I also have to subtract it. I can't just go throwing 9s wherever I want. This needs to be equal to the thing above. Right? I want this to still be that same function. So if I'm going to add this magic number inside my parentheses here so that this thing becomes a perfect square, I need to also subtract it. Another way of thinking this is one of mathematicians' two favorite tricks. One of the favorite tricks is multiply by 1. The other one is add 0. So really what I'm doing here is I'm adding 0, but I'm adding 0 in a useful and clever way, so that these three things here factor really nicely. So factor out the lead coefficient from the first two terms. Compute the magic number, b over 2a all squared. Add and subtract the magic number right after the x term inside your parentheses. Then factor the first three terms. X squared minus 6x plus 9. That's x minus 3 times x minus 3. All right, hopefully we all remember how to factor. I'll talk a little bit about AC method and factoring and stuff, but we're looking to factor just these three terms here. I'm going to leave this minus 9 off to the side. I don't care about him. I'm going to leave the plus 13, not doing anything with him. I'm just factoring these three. And if you look, 9 is 3 times 3, and 6 is negative 3 minus 3. So this is x minus 3 times x minus 3. So we factor just these. And by design, because of the way I chose this number, these will always be the same thing. Like it's always going to be x minus 3 times x minus 3, or x plus 1 times x plus 1. That will always factor as a perfect square. X minus 3 times x minus 3 is x minus 3 squared. It's something times itself. Still have the minus 9, still have the plus 13 outside. Now we can distribute the 2 and combine our like terms, and we will be done. So if I distribute this 2, I get 2 times parentheses x minus 3 squared, and then 2 times minus 9 is minus 18. So it's looking like this. Negative 18 plus 13, that's negative 5. So this is 2 times parentheses x minus 3 squared minus 5. And that, lads and ladies, is how you complete the square. So I want you to take a second and look over this procedure. Kind of ask yourself, if I had to do this on my own, where would I likely run into trouble? Is there anything here that feels at all unclear? What are we doing? Why are we doing it? Why did it come out that way? I want to say this again. You will have to do this on a test, more than one test, in fact, in this class. So there's something in the chat. How do we pick the 0? Could I ask you to be a little bit more specific there? I'm afraid I don't quite understand.
So you said that we added the 0 in there and you chose 9. So how do we figure out what number?
Yeah, right. Okay, yeah. So we're adding 0, right? And it could be in the form plus 9 minus 9, or the form plus 1 minus 1, or the form plus 7 minus 7. The number that I'm going to add and subtract so that I add 0 is always this magic number. It always follows this recipe. So you look at your original guy, these numbers A, B, and C, and you compute B over 2A all squared. That's always the thing that we're going to add and subtract. So here I wrote 0 as plus 9 minus 9 because 9 was the magic number for this quadratic.
Okay.
It's not too bad, but yeah, this step is a memorization thing. Another way you can do this, and this is how some people like to complete the square, is you just look at this and ask, what would I need to make this a perfect square? Right, so if you happen to know that x squared minus 6x plus 9 factors as x minus 3 squared, you could just look at this and go, oh, okay, I'm going to write plus 9, and then I have to write a minus 9 to make up for that. But I think that's a little tougher. I think most people do it this way for a while, and then maybe get to a place where they can see it faster without having to use that formula. All right,
What was
no
the
pressure
first
for
step again?
that. Other questions, concerns, thoughts? Mason, were you going to say something? I'm sorry.
What was that first step again?
These first two terms, I factor out a. So I know that I'm just working with the x squared term and the x term to do most of this stuff. And I really want the lead coefficient of x, I want the coefficient of x squared while I do my work to be 1. So I factor this 2 out from these first two terms. If this was 3x squared minus 12x, blah, 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 then I would have factored out a 3 from these first few terms and written this as 3 times x squared minus 4x.
I have one question.
Yeah, Dave.
Where did you get the negative 18 from?
I'm distributing this 2. So you see the big parentheses here? The reason for these big parentheses is because I factored this 2 out at the very start. I need to push this 2 back in now. I need to distribute this 2 to get rid of these big parentheses. So I'd have 2 times this. Look inside the parentheses. There's 2 terms inside the parentheses. There's this term and this term. And with this constant out front, I need to distribute it to this and to this. So 2 times parentheses x minus 3 squared is just this. And 2 times negative 9 is negative 18.
Okay, I see. Thank you.
Good questions. What else are we thinking? Okay, then we're ready to draw our graph, right? What's the vertex? What are the coordinates of the vertex? Can anybody tell me h or k?
3, -5.
Excellent, yeah. 3 and -5. Let's see. So where do I have it? Yeah, I've got it right here. So there's a kind of a minus built into the recipe here, right? This is x minus h all squared plus k. So this is x minus h all squared. So h is 3. And k is -5. All right, because the recipe here has a plus k. So my vertex, I can start drawing now. My vertex has to be at +3, -5. And that means my parabola looks something like this. Something like this. Doesn't have to be a work of art, doesn't have to be completely perfect, but it's going to be roughly the shape. I can answer those questions about domain and range now. So we've got a decent graph. This would be an acceptable graph. If this were a test, I would ask for a couple other points on the graph, like maybe find these x-intercepts or find the y-intercept or find me at least 1 or 2 other points down here. But for our purposes, because all we're looking for are domain and range, this graph is good enough. Can anybody tell me the domain?
Wouldn't it be 0, positive infinity?
So remember, the domain is all the x values on the graph, or all the x values we're allowed to plug into this function. And I'd say there's a couple ways to think of it. One way is that this arrow and this arrow, they both indicate that the function goes on and on and on like that forever.
Okay.
Right?
So it crosses over. So it's negative to positive.
Yeah, negative infinity to positive infinity. This arrow, this graph will eventually get over to the other side of the y-axis, and this one will eventually go all the way to the right as far as you want. The other way to see this is look at the algebra here. There are no domain red flags, right? There's no variables downstairs in a fraction. There's no variables underneath an even root. You could find the domain of this thing purely algebraically using the skills that we've developed through chapter 2. So the domain is definitely all real numbers because there are no domain red flags, or look at the graph. The range is a bit more interesting though. What's the range of this function?
-5 to infinity.
Very good. Yeah, -5 to infinity. And the infinity symbol always gets a parentheses. What about the -5 here?
A bracket.
Yeah, this one, the -5, I think I heard it as a bracket here. Why is there a hard bracket on the -5 instead of a soft parentheses?
Because the y value can extend past -5.
The statement there was true that the y values do not extend past -5. They don't go further down. That's not quite why we use a bracket here. Remember, the bracket means that number is included, right? So when I say that the range is bracket -5 to positive infinity, I'm saying there is a point on the graph whose y value is -5, right? This one. If this were a parentheses, that would mean we don't actually hit -5. That somehow we come down here and we get really, really close to -5, but we don't actually hit it. That's not the case. This point right here has -5 as its y value, and that is a point on the graph. So we use the bracket. Okay. Other things we could answer with this, right? Just from this kind of simple picture, I could tell you where the function is decreasing and where the function is increasing. I could tell you the minimum for the function, right? This is a local min right here. So we could say that there is a local min at x equals 3, and the min value is -5. Something I don't see from this picture, the x-intercepts, right? And those x-intercepts, they can be quite weird for quadratic functions. This is something that actually stumped mathematicians for an embarrassingly long time. So the next sort of big question, how can we find the x-intercepts? Which I will be calling from today on by the word roots. Right, so root is another name for x-intercept. There are still other names for them, zeros sometimes, or solutions to the equation f of x equals 0. You can call them whatever you want, but I'll be calling x-intercepts roots. So how do we find these things?
Wouldn't we like substitute it for 0?
Yeah, we would set the whole thing equal to 0, right? So the roots are x-intercepts. These are solutions to the equation. I'm gonna have to throw my dog outside in just a second, sorry. F of x equals 0. So you take the whole function and set it equal to 0, and then try to solve that equation. That's certainly true. But then solving that equation can be a little bit tricky. Maxwell. Hey. Come on. All right. So yeah, it's true that we find them by setting the thing equal to 0 and trying to solve, but then solving that equation can be a little bit tricky there's two main approaches. I'm sure you're familiar with these. So the answer, how do we finding x-intercepts? Roots, I get the zeros, solutions to x squared plus bx plus c equals 0. If you can, you should, so if possible, solve by square roots. For example, if you have something like x squared minus 4 equals 0, you can add the 4 to both sides and then take square roots. You get plus and minus 2. You can try to factor. All right, if you can factor that thing, then you just set each factor equal to 0. But if none of that works, you can use the infamous quadratic formula. I'm going to remind you how to factor, and I'm going to prove for you the quadratic formula. Let's do it. Find the roots. F of x. Let's do something kind of simple. Let's see, do I have a good example ready for this? So earlier, something fresh. Here we go. All right. And each of these will be able to do it by factor. So the whole solve by square roots thing, you guys know how to do this. I don't want to waste time talking about this. You isolate the x squared and then you take square roots, right? But factoring is something we might need a little bit more practice on, and we're going to be doing so much of it down the road that I want to make sure we cover this. So for that first guy, I'm trying to solve f of x equals 0, right? I'll write the 0 on the left-hand side. That means 0 equals x squared plus 3x minus 6. The way you factor this, and the way you factor any quadratic, is you look at the product a times c. So a is 1, c is -6. So a times c here is -6. Then you try to find two numbers that multiply to that product and add up to the middle number, b. So two numbers that multiply to -6 and add up to +3. Can we think of two such numbers? We need to find two numbers which add up to 3. Oh, let's see. Are we in trouble here? Do I need to change this? What was I thinking? We might be in trouble here. Let's see. Can we find two numbers whose product is -6 and whose sum is +3? Well, -6 is -6 times +1, or +6 times -1, or -2 times +3, or +2 times -3. None of those work. I think I need to modify this a little bit. Let me I'm so sorry. Change the 6 to a, let's see, to a -10. This will work. Sorry about that. All right. So we need to find two numbers that multiply to -10 and add up to +3. Can we find two such numbers?
+5 minus 2.
Yeah. So here, +5 and -2 work. And since the lead coefficient is 1, that's all we need. We can just go ahead and write down the factored form now. It is x plus 5 times x minus 2. And you can check that if you FOIL this out, you really do get this, right? X times x squared, 5x minus 2x is 3x, 5 times -2 is -10. So if you have those two things multiplying each other equal to 0, that means one of them has to be 0. So either x plus 5 is 0 or x minus 2 is 0. This is a fact of the real numbers. If you have two real numbers whose product is 0, one of them must be 0. And that means x is either -5 or x is equal to +2. So f of x is 0 if x is -5 or x is +2. Those are your roots. Those are the x-intercepts, or at least the x value of the x-intercept. This is the easier case. The polynomial does factor, right? The quadratic does factor, and the lead coefficient here is 1, so it's pretty easy. You just have to find those two numbers. Once you find those numbers, those tell you your factors immediately. The other guy, g of x, he will also factor, but he requires a little bit more work. But we still do the same thing. We got to find two numbers which multiply to AC. So A here is 3, C here is -2. So A times C is -6, and add up to 5. So can we think of two numbers that multiply to -6 and sum to +5?
-1 plus 6.
Yeah, -1 and +6. So unfortunately, we cannot jump from these immediately to our factors. So what you can do is use these two numbers to rewrite the middle term. So I'll take my 3x squared plus 5x minus 2 and rewrite that as 3x squared plus 6x minus 1x minus 2. I can do that because these two numbers have to add up to b, have to add up to 5. So 5x is the same as 6x minus 1x. And then you factor by grouping. So I kind of look at this first duo and this second duo as their own things. And I factor as much out as I can from each. So from these first two, from 3x squared plus 6x, I can factor a 3x. And what's left over is x plus 2. And from the second group, I can factor a -1. And when I do that, what's left over is also x plus 2. And if you chose these two numbers correctly, after you pull as much as you can out from each of those groups, the thing left over will match, right? So now I've got two terms. I have this term and this term. Remember, terms are separated by addition or subtraction. So this right here is not two terms, it's just one term with two factors. One factor is 3x, the other factor is x plus 2. This is a single term with two factors, -1 and x plus 2. Since these both have an x plus 2 in them, I can pull the x plus 2 out, and what's left will be 3x minus 1. And that's the job done. So g of x is equal to 0 if and only if 3x minus 1 times x plus 2 is equal to 0. And that means that either 3x minus 1 equals 0 or x plus 2 equals 0. This would mean x is 1/3 or x is -2. So this is really everything you need to know about factoring quadratics. I think most people remember how to do this. A lot of people forget how to do this. Make sure you can do both. Are there any questions on either of these? Don't be shy. Don't be shy. I was a little shaky on this factoring stuff until Calc 1-ish. So if you have questions, this is the perfect time to ask. Okay.
Wait,
Yep.
hold on, where? So you distributed the 3x and the -1?
So you're talking about here to here?
Yeah.
So what I'm doing is I see here a common factor. I've got two terms, the 3x times x plus 2 and -1 times x plus 2. Those both have a factor of x plus 2. So I'm going to pull these guys out on the right, and what's left is 3x minus 1.
Oh, I see.
It's a
Okay.
little sneaky. Yeah, I mean, I think really appreciating the kind of aesthetic here is it's not obvious. It's a weird thing to do, to factor by grouping like that, but it does work. It does work. So if this is like 3xy minus 1y, that's the same as 3x minus 1 times y. Well, here it's just x plus 2 instead of y. It is neat. Yeah, other questions or thoughts, anything at all? Okay, then the last thing I need to do for you guys is discuss the quadratic formula a little bit. I get to embarrass myself. I apologize in advance for the cringe that's going to come. The quadratic formula says that ax squared plus bx plus c is equal to 0 if and only if x is -b plus or minus the square root of b squared minus 4 times ac all over 2a. So this is a formula that gives you the x-intercepts, the roots of a quadratic, in terms of the coefficients. And if you want to remember this forever and ever, here's what you do. First, you need a human being. You need a human being besides yourself, and it has to be someone you admire, like your crush or someone in your family that you really want to like you, or someone whose, admiration you're always trying to earn. Find this person, someone before whom you can humble yourself. You know how sometimes as you're falling asleep, you get that little like tinge of a memory where you remember like something really embarrassing you did in 4th or 6th grade or whatever, and your brain's like, you're getting comfy and happy and cozy. Here's this really embarrassing memory. those are moments you never forget, right? Like I still remember telling my friend that I had this like video game and he was talking about a soccer game and his dad asked me this question. And I was like, no, I've already got this. It's fucking embarrassing. It's like a nothing thing. I guarantee you the guy forgets it. 30 years later, I remember that shit word for word, moment for moment, because it's so embarrassing. In order to remember this formula, you are going to embarrass yourself by finding this person whose admiration you value deeply and singing this formula to the tune of Pop Goes the Weasel, which I will demonstrate for you now. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. You see, you do that, and the embarrassment will be so severe that you'll never, ever forget it. It works, I promise. But something you may have not seen is where the hell this thing comes from. So this is shoved down your throat from like 8th grade on, right? Everybody knows this shit, or at least everybody has seen it. Maybe we forget some part of this, but everybody knows what this thing is. In order to understand it better, this is where pre-calc gets better than algebra classes have passed. I'm going to split up the fraction like this. Right, so we can always split up fractions over their numerator, right? Something plus something else over 2a is the first thing over 2a plus the other thing over 2a. And we're going to prove this by completing the square. We're going to take this thing and we're going to solve it by completing the square. It's not going to be bad. And out will pop this. Now you may recognize this piece right here. Earlier when we talked about going into the vertex form from the other form, I said, you know, there's a formula-based approach that you may remember. Many of you probably recognize this as the formula for h, for the x value of the vertex. So it says start at the vertex. If you want to find your x-intercepts, start at the vertex. Start at that x value of the vertex. And then you're going to walk left some distance. That's the minus. You're going to walk right some distance. And that's going to be the same distance. Both of those will be this right here. But you're going to start at the vertex, walk left and right that. What we're saying is that the roots are equidistributed about the vertex, that they're symmetric about negative b over 2a. I will draw a picture and help you see that in a minute. First, let's prove the damn thing. So where does the quadratic formula come from? It comes from completing the square. So I'm going to start with this, and I'm going to solve it in general. There's going to be lots of symbols floating around. You're going to need to be a little careful, but it's really good practice. We begin by factoring an a from the first two terms. When I divide both of these terms by a, this b becomes b over a, and the ax squared just becomes x squared. That's what I want. I just want an x squared there, not an ax squared. So to get that, I factor out the a from the first two terms. Then I compute my magic number. Oh, sorry, this symbol, I'm old enough, still means number to me. Magic number. Well, it's b over 2a all squared. And here, a is just a, b is just b. So this is b squared over 4a squared. So I add and subtract my magic number. Right here after the x terms, I'll have plus b squared over 4a squared minus b squared over 4a squared. Close that parentheses. So that you have plus c here. Now those first three terms factor. It may not jump out at you right away because of all the symbols, but I'm looking for two terms, two numbers that multiply to b squared over 4a squared and add up to b over a. Well, b over 2a times b over 2a is b squared over 4a squared, and b over 2a plus b over 2a is b over a. So the two numbers I'm looking for are just b over 2a and b over 2a. That means those first three terms factor as x plus b over 2a all squared. And then this minus b squared over 4a squared still showing. Okay. Now we're going to start solving. All right, so I've completed the square. I've got all this stuff is equal to 0, so I can subtract the c over. So my left-hand side here is still 0. I'm just not writing it. So if I subtract c from both sides, I'll get negative c equals a times big paren x plus b over 2a all squared minus b squared over 4a squared. And I'll divide both sides by a. And that gets rid of those big parentheses. Then I'm going to add this term to both sides. And that gets me here. My next big step is going to be getting rid of this square, which will mean taking square roots. Before I do that, let me put these two together with a common denominator. If I multiply this by 4a over 4a, then I can rewrite the right-hand side as a single fraction, b squared minus 4ac all over 4a squared. And it's still equal to parentheses x plus b over 2a all squared. And you start to see those familiar pieces from the quadratic formula, right? The b squared minus 4ac, there it is. My next step is to take square roots on both sides. When you take square roots on both sides of an equation, you always get a plus and a minus. So I have plus and minus square root b squared minus 4ac all over 4a squared, that whole thing inside the square root. And this is equal to x plus b over 2a. I can give the square root to the top and the bottom, the fraction on the left. The square root of the top is just what it is, but downstairs, the square root of 4a squared, that's 2a. So I'll get plus and minus square root b squared minus 4ac all over 2a is equal to x plus b over 2a. Like this. And now we're very close. I'm just going to subtract the b over 2a from both sides, and we'll have x on its own. So subtracting b over 2a from both sides, negative b over 2a, plus or minus the square root of b squared minus 4ac over 2a is equal to x. And that's it. That is our quadratic formula. And write the x on the left if you want. You can put these together into a fraction if you want. So the first time I saw this, it blew my mind. Right? I'd seen the quadratic formula for years, but I never saw where it came from. It comes from completing the square. It's not a bad argument. It's quite a nice argument. Again, this is the way I
Would we know this process?
No, not necessarily. No, I just wanted to show it to you. I want to make sure that the quadratic formula is no longer just something you're told to memorize. I want you to see where it comes from, but you're not going to have to reproduce this proof. All right, so we proved the theorem. I want to talk a little bit about the geometric interpretation, right? How you can think of this in terms of distances. And then I'll see how we're doing on time. And if there's no more time, then I will let you go at that point. So interpreting this thing geometrically. So we know what the quadratic formula is, and we know what it does. It finds the x-intercepts for a quadratic. Now somebody, I don't remember if it was in this section or another section, said to me, are all parabolas even functions? The answer is no, not necessarily. But they all do exhibit a certain symmetry. So remember, being even means being symmetric about the y-axis. Not every parabola is symmetric about the y-axis, although many are, but every parabola is symmetric about this vertical line, right? Every parabola is symmetric about its vertex. And the x-intercepts we're looking for here and here, because they are on the parabola, they are also symmetric about that line. So the distance from here to here, which I'll call d, is the same as the distance from here to here. Both of those distances are the same. So if I want to know what is the x value here, what is the x-intercept? Well, it's h plus d, where h is negative b over 2a, and d is whatever this distance is. And similarly, the guy over here, he's h minus d, because we're walking, starting at h and walking to the left d units. What is d? There. H is this negative b over 2a, and d is the square root of b squared minus 4ac all over 2a. Right? Here's h in the quadratic formula, and here's d in the quadratic formula. So the quadratic formula says start at the x value of your vertex. Start right here. And then the plus says walk to the right this far, or the minus says walk to the left that same distance. So this piece of the quadratic formula tells you how far the roots are from h. And this guy tells you where your parabola has its symmetry, about what vertical line is the parabola symmetric. So I think this understanding of the quadratic formula, start here, walk to the right this amount, start here, walk to the left this same amount, is very appealing. It helps us understand what the thing is doing and where it comes from. Formulas like the quadratic formula that tell you the x-intercepts for a polynomial in terms of its coefficients are quite special. So, just a note, comment. Formula like the quadratic formula and they're a bit hard to find. You know from your own experience that the quadratic formula is capable of spitting out some nasty numbers, right? Sometimes numbers that are not even real numbers, right? Complex numbers, imaginary numbers. people were baffled by this shit for a very long time. Later on, folks did eventually find a cubic formula. That's a formula for the roots of a degree 3 polynomial in terms of its coefficients. And even later still, there was eventually found a quartic formula, a formula for the roots of a degree 4 polynomial in terms of its coefficients. It has been shown since then, around the time of the French Revolution actually, that there is no formula for the roots of a degree 5 polynomial. Not only is there not one known, but one could never be known. The man responsible for that is Évariste Galois. He's a Frenchman. And his story is quite amazing. I'd like to share with you a little bit about Galois. Maybe before this, let me go ahead and say, okay. For general polynomials, I'm about to define polynomials. No such formula exists or could ever exist. So what do I mean by polynomial? Well, let n greater than or equal to 0 be an integer. A polynomial of degree n is an expression of the form all right, you all know what polynomials are, right? They are whole number powers of x, maybe with constants attached, added up. The way you write this out, generally I'll call polynomials p of x, p for polynomial. It's a polynomial of degree n, so the largest power of x should be x to the n. And this is allowed to have some number attached to it. Since I don't know what that number is, I'm just trying to describe polynomials in general. I'm going to call that number an. It's just the little n down here tells me it's the constant attached to this guy. And the next term is an minus 1 times x to the n minus 1. So just one smaller power of x with his own number attached. I don't know what the number is, so I call it an minus 1. And it continues down like this until you get to a degree 1 term and then a degree 0 term. The numbers, the constants, a0, a1, a2, blah, 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 all the way up to an, are called coefficients. An has a special name. An is called the lead coefficient. And a0 is called the constant term. But this is what your kind of general polynomial looks like. You've got powers of x. Those powers of x have to be non-negative integers. Each one is allowed to have a number attached to it called its coefficient, and they're added up. The degree of the polynomial is the largest power of x that shows up anywhere. So these are what polynomials are. They're expressions that look like this. Galois was able to show that for polynomials of degree 5 or higher, there could never be a formula for its roots. There is no such thing as like the quadratic formula for a degree 5 polynomial. That's a big fucking deal. Mathematicians spent thousands of years searching for polynomial formulae. And we did eventually find, obviously, the quadratic formula and then cubic and quartic formulas. But people were still working on this up until the French Revolution, looking for a quintic formula. Galois showed that no such thing could ever exist. He was 19 years old when he did this. 19, just a baby. Many of you are around that age. Very rare for someone of that age to put forth such deep and important work. And he wasn't like a well-known, respected mathematician at the time. He was more of a political figure, and he was very pro-revolution. He really wanted the revolution to succeed in France. In addition to that, he was a quite passionate man, and it turns out around the time he turned 19, he got in a fight with a dude. I think it was about a girl, actually, but there's always references to politics when you read about him. Anyway, this dude challenged Galois to a duel. Right, back in the day, this was a thing, right? So Galois and this fellow get in an argument. This fellow challenges Galois to a duel, to a fight to the death, which Galois accepted foolishly, but his pride was such that he had to. In any case, he knew he wasn't likely to survive. So the night before the duel, he wrote down some ideas that he'd been having about polynomials and like flipping the roots around, permuting the roots from one to another, and how that relates to the symmetries that he was finding in the graphs, right? Kind of like this symmetry, if you were to permute these roots, swap this root with this root, what would that do to the graph? Well, it wouldn't do anything, right? Everything would stay the same because this graph is invariant under that swap because it's symmetric about this line. More complicated polynomials have more complicated symmetries, but Galois started working with the symmetries of general polynomials and permuting the roots. He was able to, by taking the problem and transferring it over to another field of mathematics called group theory, prove that no such formula could ever exist for a degree 5 or higher polynomial. And then he was immediately killed the next morning. I don't know exactly when he discovered this work. He probably had it in his head, but the night before the duel was the first time anybody heard of him writing it down. He died the next morning in the duel, and then years later, other folks, I think, this wasn't Cauchy, I think it was Lagrange, published his work. In any case, formulas like the quadratic formula are very rare for general polynomials like these. And it's just a neat little story that I wanted to share with you, because the next thing we're going to do is start talking about polynomials in general. So the next section in the textbook that we're going to cover is section 3.2, where we're going to talk about how the factors of a polynomial shape its graph, which is kind of connected to Galois. We're going to talk about how the degree and the sign of the lead coefficient determine which way the arrows on the graph point. And we're going to slowly learn how to graph pretty much any polynomial. We've got several sections to go through the textbook here. I think like 4 sections on polynomials. We're going to be dividing polynomials. We're going to be graphing lots of things. It's going to be good fun, but it's going to also be a lot of work. So please pay attention to the homework that I post today. Try to get as much of it done as you can, like immediately. That way, excuse me, that way the stuff sinks in. And then next time, I guess on Monday, we will dive in properly to section 3.2. See what
I have a question.
Yeah.
So on the polynomial degree where you write down like an and an xn plus the rest, is that not a geometric sequence?
It's kind of like a geometric series. That's true. Now a geometric series would have all these constants being the same. And technically a series goes on and on forever, but this is very much like a certain kind of series called a power series. So if you take a power series, is like an infinite version of a polynomial like this. If you take away all the a's, if you just had x to the n plus x to the n minus 1 plus x to the n minus 2 and so on, that would be a geometric series of finite length. But with the different constants here, like this, maybe this is 3, maybe this is 5, maybe this is 12, maybe this is 13, then that would not necessarily be a geometric series. But we will be talking about geometric sequences and geometric series a little bit later in the term, so I'm glad you brought it up, but not quite. Very similar though.
I see. Thank you.
Of course. Alrighty. Any other questions, comments for me before I let you guys go? Okay, then I'll go ahead and end the meeting here. I do invite you guys to read about Évariste Galois. There's been a number of great books written about him. I think there's also like a Netflix special about him. Crazy story, incredibly bright young man. Really sad that he died so early, but he contributed this whole new branch of mathematics to the world. So truly beautiful stuff. And we will be just starting to scratch the surface of the universe that Galois' brain lived in the next few weeks. So that's it from me. Take care, guys. I'll see you next time.